Hi, I hope you can hear me. So, thank you for the introduction. The title of my talk is Current-Induced Circular Dichroism in Metallic Surfaces, where we use ab initio calculations to uh, investigate current-induced magnetism, surface magnetism in normal metals. So, the motivation is to provide a theoretical foundation for understanding um, optical measurements of current-induced surface magnetism in non-magnetic metals such as platinum, which we're going to be focused on. So what happens is that when you have a thin film, such as platinum, you pass a current, you expect that there would be a spin and orbital accumulations on the two surfaces with opposite sign on the opposite surfaces. And then when you shine this surface with with light, if the light is linearly polarized, you would expect to see a rotation, K rotation, on the reflected light. And if it's a circular light, you can see that the absorption rate between left-handed and right-handed light absorptions are going to be different. So this fits within optoelectric field if you were to um, uh, put a label on the general phenomenon. So now the question is, the conventional approach to understand this effect is to explain it in terms of spin and orbital accumulation on the surface. We use in this work, will show that we can calculate this orbital accumulation using two methods. One is the effective orbital accumulation accompanied with this circular dichroism, which I will show you how is it related to the orbital moment. And then there is another way is to directly calculate orbital accumulation using atomic orbital picture. And then we consider platinum, and then we change the thickness, chemical potential, and disorder, and see whether these two quantities relate to each other, whether they correlate or not. So the conclusion is that we find atomic orbital picture, which is typically people use to explain this effect, is inadequate according to our DFT calculations to describe the current-induced circular dichroism. Now, an introduction to the orbital Hall effect, which is considered to be the main mechanism for the measured dichroism, is that, okay, well, you all probably know what the spin Hall effect is. There is, due to relativistic effect, a charge current is accompanied by a transverse spin current, and this is due to spin-orbit coupling. Now, the way you can extend this picture and then replace your Pauli matrix for spin half to extend it to other angular momentum 1, 2, 3, and so on, and then define an orbital current, and then calculate theoretically a orbital current accompanied by this charge current. And you would see that you would always get a relatively large transverse orbital current, and that's they call it orbital Hall effect. It's non-relativistic. That means you would expect that it can be large, and but as it turns out, due to crystal torque effect and the quenching of this orbital current, it's traditionally expected that it will be short-lived, and it was expected in the old days that it would be negligible in realistic materials. But nowadays, these optical measurements are being explained by this orbital Hall effect, and the objective of this work is to really see if that is the case. So there are different ways to measure this effect. You can do it within spin-orbit torque. You could do it with the magneto-optical Kerr effect or optical circular dichroism. So now, first, let me give you an introduction on how do we theoretically treat orbital moment. There are two ways. One is the approximate atomic center approximation, where for the orbital moment operator, you define it within the muffin tin sphere, where you have more or less spherical symmetry. That means you can represent your L operators in atomic or spherical harmonic basis set, SPD, and so on, and then calculate the expectation value of the orbital current or orbital accumulation. That would be what we will be showing next. And most of the theoretical calculations so far, which are based on diffusion model and so on, based on this. Now, the more accurate approach, an exact approach of describing orbital moment is by so-called modern theory of orbital magnetization. Now, the good thing about AtC-AtG, atomic center, atomic orbital moment, is that it's by design locally well-defined. But what you're ignoring is the potential contribution from popping of electrons from one atom another, the itinerant part. But the modern theory of orbital magnetization is by definition exact. It has everything that needs to be included, and but there's a problem. It's not trivial to define it locally, and so when you write down the expression for the orbital moment in modern theory of the orbital magnetization, you end up with, you can decompose it into these two terms. The first term, as you can see, it resembles R cross V. It's your conventional classical orbital moment. But it's not really just that, because as you can see, it's expectation value of between occupied and unoccupied states and so on. So this component is called self-rotating component, self-rotating, sometimes gauge invariant component of the orbital moment. It's considered as optically active component, and some people also call it churn marker. But what we are interested in this term being optically active. What does it mean, optically active? How do we come up with this term? It goes back to the optical sum rule. If you calculate optical conductivity for this material and then integrate over all the frequency and then calculate the absorption using optical conductivity, you calculate the absorption, the circular Dichroism, which means that the difference between absorption of left and right-handed circular polarized light, and then integrate over the frequency, you would see that this expression that you would end up getting analytically would be exactly identical to this component, the self-rotating component or optically active component of the modern theory of orbital magnetism. And that's essentially the connection between the two. So what we do with the challenge here for this specific problem is that we are dealing with surface dichroism. So it's not like a bulk. So we have to consider thin film, and we have to calculate this optical conductivity as a layer resolved. So the way to do it is to define this non-local optical conductivity, where you have essentially an electric field, let's say on layer J. This is my platinum film. This is one surface and the other surface or whatever. So you have your electric field on layer J, and then you essentially calculate the AC current that is the response at layer I. We can calculate that. There's no problem with that. It's expensive, but it nevertheless can be done. But that's not all the story. I mean, we are dealing with optoelectric effect. That means we have to see how is this being modulated due to the biased electric field. And that will give us this optoelectric tensor. It's a big kind of tensor. And but this can be calculated. And since we are interested in the dichroic response, we are interested in only the dissipative part, which is odd under time reversal symmetry and so on. And it turns out that in order to calculate that, all you need to do is replace your Fermi distribution function with this non-equilibrium occupation of like a non-equilibrium F Fermi occupation, and then from that you just replace the Fermi distribution in your optical conductivity with this delta, so called F, and that would give you the change of the dielectric constant or optical conductivity in response to this external bias current, and that's what we need. Now, I said, how do we connect this using this frequency-dependent optoelectric tensor? You can integrate over frequency, take the imaginary part, and then that would give you this non-equilibrium or current-induced self-rotating orbital accumulation in the system. Right. So for the calculations, we use OpenMX, yeah, we get the tight binding Hamiltonian. It's based on a linear combination of atomic orbital basis set. So it directly gives us the Hamiltonian in tight binding form, and then we do the post-processing using that. First, we here are showing the atomic center atomic orbital moment due to the current. Here is the layer resolve for at the Fermi level for two different cases of different thicknesses, 55 monolayers thickness and 37 monolayers and so on. Here you can see that there is orbital accumulation, atomic orbital accumulation, which we use this Kubo type formula. And on the opposite surfaces, you can see that it's opposite. It has to be, the net orbital moment has to be zero on these two opposite surfaces. And so we next see how this effect, as we theoretically quite often do, is see how this orbital accumulation on the one surface changes with respect to the chemical potential. So we can see that it rather quickly saturates, like after a few nanometer, it kind of saturates to the final value. So this ACA atomic type orbital moment it's according to our calculations, had relatively short characteristic length. When you increase the thickness, it relatively quickly saturates to the net value, and it doesn't change after that. Now, this is our yes.
Farzad, I would please ask you to summarize the talk.
Yes, this is the last slide.
Okay.
So here is the frequency integrated current-induced dichroic response. Of course, it's a non-local. It's alpha IJ, so we cannot just simply plot layer resolve. So as you can see, but instead, what you can do is you sum over one index and then plot versus the other index. You can see that it's rather has a longer characteristic length, and then the other noticeable thing is that there is this surface-only non-local term, which has a much larger characteristic length, and we also change versus chemical potential, and we can compare with the ACA type orbital moment accumulation current induced, and so we can see that again. If you compare the thin case with the thicker cases, the characteristic, the dichroic response has a longer characteristic length. And so here is the summary of this work. We use ab initio calculations to calculate interlayer dichroic optical response in platinum film, and we showed that the dichroic optical response compared to the current-induced atomic type orbital moment is several orders of magnitude larger in amplitude, has different characteristic length, and it shows no correlation versus shift of chemical potential. And the take-home message is that the atomic orbital picture may not be adequate, as often people do, in describing the non-relativistic current-induced circular dichroism. Thank you.
Thank you very much, Farzad, for the very nice talk. I don't think we have much time for questions, so I will please ask you to stick around on Gather Town for some discussions.